Hey everybody, we're going to go over the related rates Desmos lab. So this is the first question you had to do. What would you get if you took the derivative of this area formula for a circle with respect to time? And again, none of these are time. There's no t in this. So when we take the derivative with respect to time, we have to treat these values as if they're dependent upon time. And what I mean by that is you would have to basically do the chain rule and chain on the derivative with respect to time of that particular variable, dA, dt, dr, dt, that kind of thing. So let me just show you this left hand side. The derivative of a with respect to t is literally that. And then on the right hand side, I have to do the power rule, so I'm going to bring the 2 down. I'll get 2 pi r. But because this is r and it's not t that I'm taking the derivative with respect to, I have to chain on the derivative of r with respect to t. And what we get, this is called a related rate. And what I mean by that is this rate is related to this rate in this way. To get this rate from this rate, you have to multiply this rate by this number. And that's how the two rates are related. This is a rate because it's a change in radius, which it would be length units like feet, inches, centimeters, whatever, per unit of time, seconds, minutes, hours, years, whatever. So this rate is changing, or this value is changing at a rate that's proportional always to this other rate. So anyway, that's what we mean by a related rate, and that's just a single example with an area formula that hopefully you're familiar with. I assumed you would be familiar with, and that's why I picked it. Alright, and this next slide is just showing you what they look like. So there's that formula, dA dt equals 2 pi r dr dt. This is just showing you that a was the radius. That's this dashed line right here. So the circle's getting bigger as that slider goes up. And then h sliding up. H was how the circle is changing. So it's changing at a certain rate. So 0 up to 0.75 units per time unit, second, minute, whatever. But notice that little green region, that's representative of the change in the radius, how the radius got bigger. So that green, the black line was the old radius. The green line is how much it changed. And because it got bigger, we added this pink region of area to the old purple region. And that's supposed to be representative of this dA dt. And it's like I mentioned in here, these are actually what we call differentials, which means teeny tiny small changes. They're not technically rates because we can actually see them, but they're representative of what the dA dt and dr dt would be. So it's the change. So as this gets smaller, the change in area is smaller. As the change in radius is bigger, the change in area gets bigger, as we would expect it to be. All right. So what this is just showing you is a kind of visualization of this area formula that we got when we took that derivative. How is the area changing? I've gained this much area. How would I describe that? Well, this is just showing you that it's just a rectangle, basically. If you cut this and you fold it out, you would get something very similar to a rectangle. It actually would look more like something like, this, because one side would be longer than the other, so there wouldn't be a nice, perpendicular edge to it. But the thing is, dA dt and dr dt, these are thought to be teeny tiny, minuscule changes. And when the change is so tiny, then yeah, basically it is a rectangle. You can think of it basically being a rectangle, because the difference between a vertical line and a slanted line, when we're talking minuscule change, just a tiny little slither, is immeasurable and ignorable, basically, as far as the area would go. So anyway, that's what this is just showing you, that is when I cut this, I get a rectangle. What is the length of this, the purple side? Well, if you look, that's the circumference of the old circle. So that circumference of the old circle is now the width of the rectangle. And then the height is that green area, which we said was representative of dr dt. So we get circumference, which is 2 pi r right there, times dr dt, the little green region. So it literally is, it's length times width. The change in area, this pink region, when I cut and stretch it out, becomes just length times width, basically a rectangle formula. And that's what these two questions are asking. The circumference of the purple circle, and then what is the area of this rectangle? The area of the rectangle is the circle circumference times dr dt, or 2 pi r times dr dt, which is, again, hopefully what you got when you did part 1. It should have been what you got when you got down here. Alright, and then the last two are just giving you some examples, or the last problem. Technically both of these were. This is an example of a related rate, and this is another very common example of a related rate. So what I told you to do, like for your hint here, was basically to stop this thing right on that being a right triangle. And so if you look at that, this guy right here over to the side, this is 5,000 feet. That's how high the plane is. And it said that this right here was 6,000. That's how far the plane is from the observer down here. So you can, with the Pythagorean theorem, you can come up with what this bottom region is. So 6,000, the hypotenuse squared, minus 5,000, this side squared, gives us this number right here. And this is 11 million. And 1 million is a perfect square. If you square 1,000, you get 1 million. So this is 11 times, remember this is this side squared. So the square root of this 11 million is the length of this side, which is the number that we're looking for. So 11. And I told you you could either round it to a lot of decimal places, so like that many decimal places, or you can use an exact answer, which again would be 1,000 times the square root of 11 was the exact answer. And that's the exact width of this side down here. So 1,000 times the square root of 11 would be this third side. Now, the question said, how fast is the plane moving away from the guy at this particular time? And it said the plane is traveling 180 feet per second. So that would be this, representative of moving forward like that. So what you had to do here to be able to do this problem is you had to start off with the Pythagorean theorem. That's what relates these three sides. And then you had to take the derivative of the Pythagorean theorem on both sides with respect to time. So d dt, I'm just going to, because it keeps doing that, I'm going to keep just put it around like that. So what you would get is 2a dA dt plus 2b dB dt is equal to 2c dC dt. Alright, and then there's all these 2's everywhere that I can cancel away on all sides and get this guy. Okay, now, what's what here? Well, this right here, this red arrow, is representative of the change in this length right here. Well, that's this same length down here, which, we call it A or B, it doesn't matter. Let's call it A. So that's dA dt, which would be the 180 feet per second. Okay. A, which is, this length right here, that's what we just solved for. That's the 1,000 square root of 11. So this number right here is A, 1,000 square root of 11. All right, B dB dt. Remember the Pythagorean Theorem, this is A, B, and this is C. So this is B, 5,000. But what's dB dt? That's the change in B over time. Well, it's flying at a constant 5,000 feet. What's the derivative of a constant? The derivative of a constant is 0. So this whole entire piece, because of the multiplication, will just go to 0. Alright, and then finally C, that's this guy right here, that's 6,000. And then what's dC dt? Well, we don't know that. That's what we're trying to find. That's what we're trying to solve for. So dC dt, that's what we're trying to isolate. It's equal to this A, which is the 1,000 times the square root of 11 feet. There's the dA dt, that's how fast it's moving forward, though 180 feet per second. And again, the other piece was 0, what we ended up with, and that's equal to the 6,000 times the thing we're looking for, dC dt. So there's a quick solution. We just solve it for dC dt by dividing away the 6,000. Alright, and so the 1,000, the 6,000 will reduce to 6. 6 will go into 18 3 times, and we're left with 30. 3 and the 0, square root of 11. Alright, and this is 6,000 feet also. That'll cancel with that. So we're left with feet per second again. So there was our exact answer. 30 times the square root of 11 feet per second, which you can also have given me a decimal, which I believe was like 980 or something like that, or 99.5 roughly. So about 99.5 feet per second is, and what does that mean? What have we just found? Every second that goes by at this moment in time, for every second that passes, as this thing's moving away, right at this moment in time, this snapshot, this blue line right here is growing at a rate of almost basically 100 feet every second. Right, 99.5 feet per second roughly, but that's the interpretation, is that distance between them, that diagonal distance, is growing at almost 100 feet per second at that moment in time. Alright, and then the other question dealt with the angle. How fast is this angle growing? And this one right here, the thing that you needed for this particular one, this down here is our theta, and we're trying to find out how is this angle growing at the moment that we reach this 6,000 foot marker. So what rate is that angle growing? Okay, well, again, I called this A, I called this B, and I called this C. Well, in this little triangle right here, I could also move this A from the bottom up to the top, and now I've got two sides of a triangle, a right triangle. And I know their values. I know a trigonometric function I can set up that deals with these values. This is the opposite side of that angle, and then this is the hypotenuse. So who is opposite over hypotenuse? If you remember your right triangle trig, this is the sine of the angle. Okay, so that's what I set up. The sine is equal to A over C in this case, with what I've, the way I've got it worded. And I need to do the same thing. The derivative with respect to time on the left and the right. So sine of theta, if I take the derivative of that with respect to t, and then I take the derivative with respect to t of a over c. Alright, what's the derivative of sine? The derivative of sine is cosine theta, but I have to chain on the derivative. Alright, and then that's equal to this guy right here. I'll need the quotient rule. So low d high, that'll be c times dA dt minus high d low, so that'll be a times dc dt, right, all over low c squared. Okay, so there's the setup. It's the sine function, the derivative of both sides with respect to t. I've got chain rules and quotient rules and trig rules, all kinds of stuff going on. Alright, and now I plug in what I know and solve for what I don't, which I'm trying to find how this angle is changing. And there it is, d theta dt shows up in the solution. Alright, the cosine, go back to your picture. Cosine of this angle is adjacent, alright, which is 5,000 feet, over hypotenuse, which was 6,000 feet. So the cosine is just 5/6. Alright, times d theta dt, again what we're trying to solve for, is equal to, now we plug in what we know. This is, c is 6,000 times dA dt. If you go back, dA dt was how fast this plane is moving forward, how fast this horizontal distance is growing, and that was 180 feet per second at that moment in time. Alright, minus a, again a is our value here, which was what we got on the last problem, the 1,000 times the square root of 11. And then dc dt, that's what we just solved for on that last problem. That's why I wanted you to do that problem first. So the 30 square root of 11. So times 30 times the square root of 11. And then that's all over c squared, which again, c was our hypotenuse, so that's 6,000 squared. Alright, so to isolate this d theta dt, I multiply both sides by 6/5. Alright, think about that. That would cancel everything there and leave you d theta dt. So that's where this 6/5 came from. And then these two multiply to 1,080,000. These two expressions multiply to just 330,000. I subtract those two and I put them over 6,000 squared is 36 million. And then I just simplify. So we get 1 over 40, and these are radians per unit of time, which in this case was seconds. So 1/40th of a radian every second. And if you remember, if I take 1/40th and multiply that by, that's radians. So if I go to 180 and I divide by pi, that would be degrees now. So about a degree, 1.4 degrees, roughly, every second that passes. So 1.4 degrees. For something probably a little more familiar to you, but that's what you have to do in a problem like this. You have to set it up, the trigonometric function, depending upon the picture, what the picture looks like. So opposite over hypotenuse, so I set up sine, and then take the derivative with respect to time. Derivative of sine is cosine, quotient rule on the right hand side, and then just start plugging in your numbers and know what to isolate in a problem like this.